Hey guys, this is Josh Myers and I'm back, and as we can see, this setup we have here leading into this video is the exact same setup as we had at the end of the last video. And the first thing that I would like to focus your attention on leading into the subject matter of this video is the idea that a trend is a general rule. It is a general rule, and what that means is that it has exceptions. And so when talking about any sort of exception, there's always some rationale behind it. There's always some special case that breaks the underlying rule of any statement. And so the exception that I would like to bring to your attention today, before I wrap it up for the night, is the idea that, as we know, the ionization energy decreases down a group, and it increases across the period. However, if you go to period 2 and we compare the ionization energy, so the IE of nitrogen and the IE of oxygen, and what I'm referring to here is the energy required to release one electron from nitrogen versus the energy required to release one electron from oxygen. This specifically is the valence electron, and we will get a better understanding of exactly how these electrons are released in this video. But the exception to the general rule that as we go across, the ionization energies will increase by 1 each time, will increase as you move to right each time, is broken by saying the ionization energy of nitrogen is greater than the ionization energy of oxygen. And as we know, oxygen is further to the right, and thus the rule is broken. So why is this an exception? And this is what we're going to talk about in this video, where we talk about orbitals. So let's erase this big title we had here. It's stood strong for a very long time, but now it's got to be dethroned by the orbitals title. All right, hold on. Let's get this all erased. Okay, very stained board now. Okay, we are working hard. Okay, so now this is the video on molecular. Oh no, that is bad. That is a bad M. Molecular orbital theory. And the reason why we have theory here is that it is not necessarily something that they 100% understand, in the sense that when scientists describe orbitals and what comes underneath the atom, they have very strong evidence to suggest one theory or another, but it is not quite as solid as something where we were talking about, do atoms exist or not. We are almost certain that they exist, whereas when we talk about any sort of theory, molecular orbital theory, it is much more acceptable to question this sort of theory, and they do this from time to time. So anyways, we are going to talk about molecular orbital theory. Okay, and so the first thing that we've talked about this idea a lot of orbitals as we've gone through our videos, and I've alluded to this idea of what is underneath the energy level. To this point, even in the last video, I am teasing, saying that the accepted way of drawing these atomic structures is through using the circular orbitals, the ones that literally orbit the nucleus in circular motion, and these are the only paths that the electrons can take. And I have alluded to the idea that this is wrong. This is not technically correct. And I have not lied to you. It is not technically correct. And this is how we are going to look at this video moving forward, is what is the more technically correct answer. I'm not saying it is the absolutely technically correct answer, but I'm going to tell you it is much more technically correct than these nice, pretty circles we have been drawing. But unfortunately, science is not pretty. It is true. It is. We do not do science to make it pretty. We do it to make it true, to make facts that we can know our physical world by. Okay, we're almost done erasing, and we can start doing this thing. Okay. All right, let's get rid of all these smudges. All right, I spent about 30 seconds erasing, so now I have to start talking again. Otherwise, this channel might just corrupt itself. Okay, so molecular orbitals. And so this is the idea, as I've discussed, of the what is underneath, the idea underneath the energy level. The energy level. And this is why we are going to eliminate this idea of energy levels being circles today, because we are going to talk about what is underneath them as stated here. Okay, so just throwing this out there right off the bat, because there's no easier way to introduce it than to say that there are two main types of orbitals. Two main types of orbitals. They are variables, but that's not what I meant. That's what I was saying, though. Two main types of orbitals that we will draw pictures of. Two main types of orbitals. And when I say main, I just mean that they are the ones that we will have pictures of in our head and that we will be doing most of our work on throughout this chemistry channel. Okay, so one of them, as we refer to, we've denoted it as the S orbital. And it has, it has the circular shape. And so, we haven't been wrong so far. So far, we have been drawing S orbitals properly when we have drawn our atomic structures. But then we move into p orbitals. And p orbitals are a little bit more tricky because there are three types of p orbitals. And it just keeps getting more complicated, I know. Stick with me. Py, px, py, and pz. Okay, and their pictures. Let's think about their pictures for a second. Okay, so px, all p orbitals. Let's talk about the general p orbital rule. All p orbitals have the shape of a dumbbell. If you are a big gym rat, you will understand this. They have this shape with two loops that are created in a sequence, in a line sequence. There are two loops that are created in a single line sequence. Let's make these solid lines, because that's what orbitals are. They are solid lines, and we will talk a little bit more about exactly what these mean once we find out what px, py, and pz are shaped like. Okay, so relative to a normal, if we are talking about a vertical line coming down from the nucleus relative to a normal, px dumbbell, if we're talking about dumbbells instead of orbitals, px dumbbell is shaped like this. It is vertical to this normal. It is perpendicular to normal, if you want to speak about it that way. It is perpendicular to the normal. And then py orbital is the problem child. It is almost exactly diagonal to the normal. It's not sure which way it wants to go, horizontal or vertical. And so, finally, the pz orbital relative to the normal. Ooh, I might need more room for this. Relative to the normal, it is horizontal relative to the normal. And so now that we have these pictures, let's talk a little bit about what exactly these shapes represent before we start applying these pictures, these s orbitals, these p orbitals, and later what we talk about with d orbitals to the periodic table. That's why I kept this thing up here so that we could use it now. Okay, so what do the orbitals represent? Well, there is an abundance of physics research that has been done in the last 100 years on exactly what an electron does underneath the atom, what it does in its energy levels, what it does in its orbitals, what it does in this idea of the orbital. And what the orbital truly is, how they've determined its shape, because you're thinking, Josh, how would they possibly know something that small within the energy level, this absolutely outrageously minuscule thing, the energy level, and know within the energy level how the electron is moving, in what sequence, in what path it is moving? And my answer to you is these orbital shapes are simply representations of this thing called a probability function. A probability function, and what this says is this idea of the probability function is that the electron can't be, the velocity and the position of an electron cannot be determined at any point in time, both of them together. And so the same idea applies to this sort of orbital shapes, is that these shapes represent the idea of a probability of the electron being somewhere in this sort of shape within the energy level. And this is where, guys like Schrödinger came up with the idea of the wave function, in that an electron, because it is a mass, because it's a very, very small mass, it has a wave function. And that electrons, when traveling through energy levels, behave this way in such a way that they are continuous, that they aren't just a single mass, that they are continuous in this thing called the wave functions. They are continuous, and they make up this entire orbital. They are literally everywhere in this entire orbital, or at least according to some quantum theories, this is exactly what is happening. And so until they are observed, until their position can be known by some measurement, they are, to us, literally everywhere in this molecular atomic orbital. When I say atomic, I mean in the atom, but this is called molecular orbital theory. Okay, so now that we have that off our chest, that isn't necessarily important for this channel, that is more of a physics concept, but just so we understand exactly how these orbitals came to be discovered and what they really are, rather than just an idea that we're drawing on this whiteboard and just an idea that we are going to now start to apply to the periodic table. So now we are applying. Let's apply. Okay, I like applying myself. That is how I believe I have come to know certain chemistry things in this world. Okay, so in order to make this easier for ourselves, let's do some scrappy erasing. And I feel like this entire video I have been erasing, but such is life. You have to start over after you make mistakes. And I don't think that I need to give you guys any life lessons. You guys are all very smart people by watching this video as it is. So I think that you can guide yourselves in this crazy world. I make silly decisions anyways quite often. Okay. Alright. So now, how do these orbitals, this S and this P, the two ones that we have introduced so far, apply to the periodic table? Well, let's start with the period 1. Let's start with period 1, hydrogen and helium. Hydrogen and helium. And these two elements represent two electrons in the periodic table. They represent the first 2 electrons. And so hydrogen has 1, helium adds, when you add to helium, go to helium, from hydrogen to helium, the second electron becomes present. And as we've discussed, as we've seen before, as we've visualized before, I'm looking for the right words here, visualized before, we have seen the circular energy level that has 1 electron here and 1 electron here. Well, here what is really happening is that these 2 electrons are part of the 1s orbital. And when I say 1s, it is because they belong to the first energy level, and the orbital that they belong to is the s orbital. And so why this is important exactly is that we have a situation where if we were to move to the second energy level, the first two elements, lithium and beryllium, they would also be part of the s orbital, but in this case they would be the 2s orbital because they are in the second energy level. And so let's pick out one more example. Here, if we were to go to the third energy level, sodium and magnesium, they're added electrons. So in this case, when we are progressing through the periodic table, we are talking about these elements in terms of adding 1 more electron. So the 2 electrons that are added when you move to sodium and then progress to magnesium are part of the 3s orbital, the s orbital in the third energy level. So what are we seeing here? We are seeing the idea that hydrogen and helium are paired, lithium and beryllium are paired, and sodium and magnesium electrons, the electrons that represent them in this case, are paired in s orbitals. And so this, let's make a big rule here because this is very, very important. This general rule for this type of pairing can be given that each orbital contains a maximum of 2 electrons. Each orbital contains a max of 2 electrons. Okay, and you can still see, I hope you are still following this video because it has gotten a little bit more complicated than all of the other ones. Okay, so now we've established the idea that each orbital contains a maximum of 2 electrons. So far we've only talked about the s orbital. And so now what we need to introduce next is the p orbital. And the p orbital represents this block. It represents this block, the nonmetals and metalloids block of the periodic table. So that is p. And as we've already discovered, the s orbital represents the metals portion as well as hydrogen and helium. So 1, 2, and then the metals portion is represented by the s orbital. S orbital. Shoot. Oh gosh, I am just so tired right now I can't even write. Fortunately, I can still speak. That is a good thing. Okay. So s orbital. Yeah, s orbital. Okay. Alright, so these nonmetals are represented by the p orbital. And as we know, there are 3 types of p orbitals. They are px, py, and pz. And now we will focus on, as we've stated here, each orbital contains a maximum of 2 electrons. And so if we were to think of this p as just the general p, there are 6 elements that would be contained within this general p. So that means that there are 6 electrons contained within this general p. So how does this apply to the three types of orbitals? Well, so if there are 6 elements in this P, and there are 3 types of orbitals, then that fits our rule exactly, because if 2 electrons fit in each type of orbital, and there are 3 types of orbitals, then there are 6 electrons, and that is exactly consistent with the number of elements that I am saying fit into the P, what we call the P sublevel. What would be called? That would be called the P sublevel, and the S sublevel. The S sublevel. Let's not say orbital, let's say sublevel, even though technically it is, there's only one S orbital in each S sublevel. So I didn't technically make a mistake, I make many, but that wasn't technically a mistake. Okay, so let's give ourselves a little more room here, and then we are going to talk about which ones are which. So which elements are which for the PX, PY, and PZ. So these 2 elements are PX, these 2 elements are PY, and these 2 elements right here, oh gosh, it's so hard to draw these arrows, are PZ. And this will mean that for these elements, let's talk about, say, the boron-carbon pair. This means that they are in the boron-carbon is in the 3px. The 3px orbital. The last electrons are represented in the 3px orbital. 2px orbital. If we were talking 3px, we would talk about aluminum and silicon. That is 3px. And we see exactly how, as we go down the periodic table, the energy levels are changing, but vertical rows, the groups, are simply still represented by the exact same orbital. So now this video is getting quite long enough, but in the next video we will discuss the idea of the orbitals possessing particular energies and how this applies to the filling of them, in which we will talk more about. There's many different types of rules for the filling of them, and then we will finally get our answer about this magical exception that we discussed at the beginning between the ionization energies of nitrogen and oxygen. Alright guys, see ya.